we will go through again the process, and you will see that it is so this is a simple example with a frame fixed at A. Then you have vertical member AB 10 meter high, and then you have something like a cantilever member BC 7 meter. And you have point load here and UDL here 20 kilonewton meter horizontally. So here, if we check statical determinacy, this one you should have no problem to check. So this one, I think 3 unknown forces at the support, 3 equilibrium equations, so statically determinate frame. Okay, so checking means you have to do like this and then make the statement here. And if it is statically indeterminate, then you have to give what is the degree of statical indeterminacy, class. So next is, now here, normally if we can choose to start from one particular side, if you choose wisely, then we don't have to determine the reaction force. Okay? Because if we cut here, we have this free body diagram. If you use this, then you have to use this reaction force. But if you use this to get the shear, axial, and bending moment, we don't have to calculate reaction force. So this is one example. This is one example. Okay, if we choose to proceed our calculation from C, you cut here, then you take this part. You cut here, you consider this part. You don't have to calculate the reaction forces. So this is how we are going to proceed for this example. So how many times we have to cut here? 2. Yeah, you have to cut 2 times, twice here. Once along this member, once along this member. So we start from C, not from A. We don't calculate reaction forces. So here, yeah, for member BC or portion BC, so we cut here. We don't use this part. We use this part. So this is a simpler free body diagram. But then please take note of the positive shear, positive bending moment directions. This is similar to the case of beam because the member is horizontal. So shear is in Y direction. So you use the equilibrium equation in Y, then you get shear is positive 80 constant. Bending moment, take moment at the cut section, and you get bending moment is equal to negative 80, 80x. So shear is constant, bending moment is a straight line. So if you try to draw for this part, so this is the axis of the member BC, axis of the member BC. So positive shear constant and negative bending moment all the way, negative straight line until C. C is a free end, so bending moment should be 0 there. So the next part is we come to here, then we use the free body diagram of this one. So if you look at the next part, for BA now, portion AB, so we cut here, we use this free body diagram, okay, which is shown here. So the shear positive is, and bending moment positive is in this direction, as shown there. Then the shear now is in x-axis direction, is in x direction now. So you use your equilibrium equation in x. So if you do that, then you get S is equal to 20 multiplied with x here. This is x. So then proceed to bending moment. You take the moment at the cut section here. Then the moment caused by this, moment caused by this. So that is the result. So moment become a curve, a parabolic curve. Shear is a straight line. So bending moment will become a curve. So if you draw now, okay, this is axis AB, this is axis AB. Shear is a straight line. All the way from B to A is positive, but 0 to 200. Then bending moment is all the way negative. Yeah, from the equation, we get all the way negative. At B is negative 560, at A is negative 1560. So if you combine, yeah, don't forget, after you finish part by part, you have to draw the final shear force diagram and bending moment diagram. Shear force diagram, bending moment diagram, and this is the shear force diagram and bending moment diagram for this frame example. Qualitative deflected shape. If you want to draw qualitative deflected shape, then before that we go to axial force. Axial force for this part, if we cut and then we use that free body diagram. So positive axial force is as shown in the diagram there. Then we get, there is no load in the direction. So for member BC, there is no axial force. For member BC, no axial force. And for member AB, if it's for member AB, then we make use of this free body diagram. This is a positive shear, positive axial force directions. And from the equilibrium equations in y directions, you get Q is equal to negative 80. Q is only affected by this. This one is direction perpendicular to Q. This one does not affect Q. This one affects the shear and bending moment. But this one does not affect Q. Q is only affected by this. So Q become negative, which means that member is in compression. So this will be the combined axial force diagram for this frame. This B to C is 0, then AB is negative 80. So we draw on this side because this is the plotting. This is where to plot. Positive is here, negative is plotting over there. So axial force is negative. That's why we plot on that side, yeah, on this side here. Now here is to show to you if we calculate the reaction force here, if we know the reaction force here, this is very easy to calculate. If you know the reaction force here, then we can use this free body diagram to calculate the axial force for this member. Just now we use this part. We can also use the other part, which is easier, but you get the same answer. You get the same answer, but in this case, because we do not calculate the reaction forces, that's why we use the free body diagram, the other part. If you calculate the reaction force, then you can use free body diagram as shown there, okay, to get the Q, and you get the same result. Q is negative 80. So qualitative deflected shape class, just to get you familiar with qualitative deflected shape for frame. Remember, bending moment diagram is drawn on the compression side. So the dotted line there, I indicate which part is in compression. It follows the bending moment. Then, if that is compression, so this one should be bent like this. This one should not move. And the slope should be 0 here because this is fixed. And this one is compression bottom, so it should bend like this. Then here the degree should maintain because this is 90 degrees. Yeah. At joint B, you should maintain the 90 degrees. So that is the qualitative deflected shape that we get for the frame. Make sure that this one stay at the same place because this one cannot move, cannot rotate, yeah. And bend compression this side, and then this one bend compression down. And this maintain here 90 degree after it deflects. So here, just to indicate to you which side is in compression. It is on the side where you draw the bending moment diagram because we draw bending moment diagram on the compression side. So it's on the side of the bending moment diagram. So that side is in compression. So class, that previous example is not is just a go through again the process. Okay. Now we come to this example where the member is inclined. Yeah. Where the member is inclined. So again, the question asks you to draw shear, bending moment, and axial force diagram, and also sketch the qualitative deflected shape for this frame. This is just now we have vertical, horizontal. Now this vertical incline now. Okay, and how much is this inclination you can get from this dimension here? This is 4 meter. This is 3 meter. So you can get what is the angle here, or later the sine cosine. And this is 4 meter, 3 meter. The length of this is 5 meter. And this is 6 meter high. This is fixed here. And the load is vertical. Yeah? The load 10 kilonewton meter is vertical. Is acting vertically, but distributed over member BC. So this one, this is checking statical determinacy. You don't have the, you shouldn't have any problem now. Okay, so again, if we start from this C here, the calculations, we don't need to calculate reaction forces. Here, how many cut? 2 times. 2 times cutting we need to do, which is cutting one along member BC and cutting ones along member AB, which is section AA and section BB. Now, let's start with this here. Okay, you cut through here, then you use the free body diagram of this part here. Now the load is like this. Okay, but this is member is inclined. So the axial force and shear force also incline now. It follows the axis of the member. So that is the main point that I would like you to get from this example. So we have 2 set of axes now, x and y, which is here, x and y. The other one is x prime, y prime. This x prime is follow this axis direction. This y prime is 90 degrees to the x prime. So there are 2 axes, xy and x prime, y prime. Okay? That we need whenever we want to define the direction of the axial force and shear force of this member. So this is the important part that I want you to be able to get from this example. Okay. Now, you look at the diagram. You look at the diagram. If you look at the diagram, this one here. Okay. Now, the red arrow which is indicated here, the red arrow which is indicated here is the direction of the shear force. Positive direction of the shear force. Okay. So in order to determine the positive direction of shear force in this direction, we have to write down equilibrium equation, follow that inclined directions. You have to write down equilibrium equation, follow these inclined directions. Okay. To do that, you need to find the component, the component of the loading, everything in these directions. So we start with this distributed load. Distributed load is vertical. Distributed load is vertical. So we have to get the component which is perpendicular to the member and parallel to the member. So that is being calculated in this diagram here. So the inclination of this member is 4, 3, and 5. This is from the dimensions given to us. This dimension is 4, this dimension is 3, this is 5. So this inclination here can be calculated from this triangle. Okay. And to calculate the component of this and component of this, you need to know this angle. Yeah, you need to know this angle. You need to know this angle. Okay? This angle, if you know this angle, then this tan cosine, this angle, you get this. Tan sine angle, you get this component. Tan multiplied with cosine, you get this. Tan multiplied with sine, you get this. So this angle is the same as this angle here. So from there, we get the component which is perpendicular to the member is 10 multiplied with 4 over 5, which is 8, which is indicated here. And for this, which is not indicated in the diagram, which is a component parallel to the member, is 10 multiplied with 3 over 5, which is 6. So this is the things that we have to calculate whenever you have an inclined member and the loading is vertical, then you have to get the component of that loading in the direction perpendicular to the member and in the direction parallel to the member when we want to calculate shear force and axial force. So this is one thing that we have to take note. So after we do this, so we are going to get this. Okay. So this is what we get from 10 kilonewton per meter, which is vertical. We get the component which is perpendicular to the member, 8 kilonewton per meter, the red color that I shown here. And you get the one which is parallel to the member, which is 6 kilonewton per meter in the direction of the green arrow. The green arrow direction is the direction of the axial force. This is the direction of the shear force. You need to do this because when you want to calculate shear force, you need to write equilibrium equation in these directions. Axial force, you need to write equilibrium equation in these directions. So this makes the calculation of frame a bit lengthy, a bit complicated. Okay. So once we have settled that, then whenever we want to calculate shear force, we need only to consider the component of the load which is in the direction of shear force. So the component of the load in the direction parallel to the members will not affect the shear force. So we don't show the component parallel to the member. Okay, so by using this free body diagram, then we can use equilibrium equation in y prime directions. In y prime directions, follow the S. Follow S. So we get the shear is equal to 8x, which is a straight line. Then for bending moment, look at this free body diagram. For bending moment, then we get the bending moment is equal to negative 8x multiply x over 2, which is negative 4x squared. So this is the equation for the inclined part there. And there is one note here, okay, class, only components perpendicular to axis of member affects the shear and bending moment. The component which is parallel is not shown here because that will not affect the shear and bending moment. That will only affect the axial force. So only components perpendicular to axis of member affects the shear and bending moment. So this is one point that we need to take note. And how do we get this 8 kilonewton per meter? So we have settled here, settled this part here. Now we go to this vertical part. Now before that, if you try to draw for this part only, so that is the shear force diagram, that is the bending moment diagram. Shear force diagram and bending moment diagram. The shear is straight line, 40 until 0. And then bending moment is curved in this way. If you look at the slope of bending moment is equal to the shear force there. So this is positive slope decreasing until 0. That's why it is curving in this way. Yeah? Positive slope, positive, 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 decreasing until 0. Shear 0 here. So that's why it's curving in this way. And it's negative 100 kilonewton meter at B here. Here, try to remember this. This is a very helpful relationship. The slope in bending moment diagram is equal to shear at the same point. So we know how it should curve. Okay? If you look at the shear force diagram and make use of that relationship, dm dx is equal to S. So we have settled with this member, class. Now we come to this member here. So we cut here, then we make use of this free body diagram. Because we do not calculate reaction force, we cut here, we make use of this. So that is the next step. And that is the free body diagram. The loading is in vertical directions. We show in vertical directions. Then for shear, when you calculate shear here, class, the shear here now is in these directions. Positive shear, positive bending moment. So this is in vertical, so this has nothing to do with shear now. So we maintain this as vertical directions. This is in vertical, this is in horizontal, so this has nothing to do, this will not affect the shear now. So we maintain this, we don't need to get this and this here. Okay? When you want to calculate shear force, axial force, yes, we have to get this and this. But for this member, because the shear is like this, then this one does not affect this. So we maintain this in vertical direction. So we get the shear is equal to 40 kilonewton. Bending moment, okay? Bending moment next. Now, we go back to the definitions of moment. Moment is force multiplied with perpendicular distance. So when we want to get bending moment at this point here, caused by this loading, so we just try to find out what is the equivalent load, and it is acting vertically, then multiply with the perpendicular distance. So here we don't need to change to this component and try to find a moment, but you can maintain like this because from here, if you want to take moment here, this is vertical, then multiply with this perpendicular distance. So there is no need to change this into this and this when we want to calculate the moment for this member. So that is how the calculation is done here. Then we get, this is constant, so bending moment become a straight line. So if you try to draw, then this is what we get. Shear force constant positive, bending moment is straight line, and it follows the slope here. These are all positive slope. It follows the slope like this. Or straight line, you just get what is the value here, what is the value here, you connect, then you get a straight line. That is for part AB. Combine them. Don't forget, finally, you have to combine them. So this is the final answer for the shear force diagram and bending moment diagram and the original structure. Okay. . constant here, straight line here, straight line here, curve here. Okay. Then the qualitative deflected shape. So qualitative deflected shape, look at the bending moment diagram. Where is the compression side? How the frame is supported. Okay. Before that, always forget this axial force. So axial force now, cast. Axial force, you look at the comments at the red color there, only component parallel to member axis will affect axial force in that member. So there's only 6 kilonewton per meter. The one parallel to the member axis will affect the Q. The one perpendicular is not shown there, will not affect. So from that free body diagram, we are going to get Q is equal to -6 multiplied with X. Only that will affect the Q. Then for this part here, for this part there, okay, the Q, positive Q is in this direction. So Q plus this equivalent of this is 10 multiplied with this length, which is 50. So we get Q again negative. So it means it's in compressions. So if you draw the axial force diagram, if you combine them, so this is what we get. Okay. For BC is straight line, -6x. And for AB is constant, -50. So this is the axial force diagram, the complete one. And here, just to show you the this is I don't know how to explain this, what is the meaning of that thing, but this is asking for your attention, okay? Asking for your attention. Please pay attention to BC, 6 kilonewton per meter, AB compression 50. So this is using cut sections. Cut here, use this part here. If you calculate the reaction forces here, then you can use this part. Here we don't calculate reaction force. That's why we use this part. But if you calculate reaction force at A, then we can use this free body diagram to get the Q in member AB. You get the same answer. So qualitative deflected shape. So by now, class, look at bending moment diagram. Where is the compression side? Is on the side where you draw the bending moment. So the frame should bend as shown in this diagram here. Compression happen on the bending moment diagram side. A is fixed. Then angle of BC. So you see, we indicate this. This is to make sure that the angle here before and after you maintain. Okay? You maintain here. Bend like this, compression bottom. Bend like this, compression on this side. Follow this bending moment diagram. Now, there are two different ways of drawing bending moment. Yeah. What we're using here is bending moment diagram drawn on compression side. But there is also bending moment diagram drawn on the tension side, which is you just change this to the other side. This one change to the other side. It looks something like this. Okay. What we draw is this one. Now there are some exercise here that I would like you to go through to try to draw the shear force bending moment diagram and also try to draw the axial force diagram and qualitative deflected shape for these two examples here. Okay. This is the same type of frame, but then the loading is 90 degrees here, and there's a point load here. Here, again, same vertical and horizontal member, there's a point load there. So first, how many cuts we have to do here? How many cuts? How many? In each member, basically you have to cut once, but in this member there is a point load here, so you have to cut here once, and then here once. Okay, here one time, here also 3. So class, try to get this. I will give you the answer for that, the final answer for that. Try to compare whether you get. Try to compare your answer. But this is 90 degrees. Okay, this load is acting at 90 degrees to the member here. Now, the last example that I'm going to go through with you is also an example where we have inclined member. But that example, we can make use of one of the characteristic of that example, which is it is symmetry. So when it is symmetry, we don't have to draw shear force diagram, bending moment diagram for the whole part. We just need to draw one part, then the other part we can draw according to the characteristic that it is a symmetry problem. Okay. So what is the meaning of that is I'm shown using this diagram here. Now, sometimes we can make use of symmetry, the problem of symmetry, to save time in drawing shear force diagram and bending moment diagram. I give you one example which is symmetry, which is a beam supported here, and loaded right at the center. So this is a symmetry problem. The structure shape is symmetry. The loading is symmetry, right at the middle there. So if you look at the shear force diagram, is like this, and the other side is like this. Bending moment diagram is like this, and the other side is like this. So that means that you just need to know what is the shear force diagram or bending moment diagram on one side of the axis of symmetry. Then once you know this, then you can know the other side here if it is symmetry. So this is axis of symmetry of the problem. Then how do we get? You just need to calculate this side. Then the other side, you can just do some rotation or flipping. Okay? Look at the shape of that shear force diagram and bending moment diagram. So what we do here is, first, to get here, first you flip this over here, then you flip over there again, then you get this shape. And if this is positive, on this side become negative. So bending moment, once you know this thing, once you know this side, then you flip over to that side. So you complete the whole bending moment diagram. And whatever positive here, here also positive. Whatever negative here, also negative. But here is not complete yet. Here is completed. So you just need to determine one side, then you can get the other side. The other side of the axis of symmetry. To get the complete shear force diagram, you have to do 2 steps here. One, you flip to this side. And after that, this one you have to flip over this side again. Then whatever positive here, here become negative. So shear force diagram, bending moment diagram has this kind of characteristics that we can take advantage of for problems which are symmetry. So we can save time, no need to calculate the whole thing because we know their characteristics if the problem is symmetry. For axial force diagram, okay, and another example is this. This is a frame which is symmetry problem. The shape is symmetry, the loading also symmetry. So the axis of symmetry is this. And if we draw the axial shear force diagram, this is the shear force diagram that we will get. And this is a bending moment diagram that we are going to get. So you just need to decide, take half of this, determine the shear force diagram for this part, and bending moment diagram for this part, and also axial force diagram later on. Then you can complete to draw on the other side. Okay. So bending moment diagram, if you know this shape, so the other shape is completely symmetry, just flip it over here so you get the complete shape. And whatever positive here, you also get positive. Whatever negative here, you also get negative, the same. But the shear force, you have to do 2 times. So you flip over here first, and you get like this. Then you have to flip one more time. This one flip down, this one flip to the other side. Then you complete to draw the whole shear force diagram, okay, on the other side as well, and you complete the whole thing. So this one, after you flip, this side you flip through again, so you complete, you get this. But for shear force diagram, whatever positive here on this side become negative, whatever negative here on this side become positive. So this is taking advantage of the characteristics of the shape of shear force diagram and bending moment diagram for problems which are symmetry. For axial force diagram is the same as the case for bending moment. If its problem is symmetry, then you draw only one side. Then look at the axis of symmetry, then you flip on the other side, then you get the complete axial force diagram. So whatever positive here on the other side also positive, whatever negative here on the other side also negative. So similar to the characteristics of bending moment diagram for problems which are symmetry. Of course, I think if we don't want to take note of this, we can calculate the whole thing. But if you know the characteristics, we can save the time. And also, if you know the characteristics, we can also check your bending moment diagram. For symmetry, it should have certain characteristics of the shape if it is symmetry. So here, we take note that it is symmetry, so we calculate only one side to save the time, and then we do the flipping here. Because it is symmetry, then we can complete the other side. So we save time in the calculation. Okay. So this is one characteristic that we are going to make use of in the final example. Okay. But now it's almost 10:30, so I do not want to take more of your time. So now this problem here has characteristics of symmetry. This 4 meter, 4 meter. Okay, this right at the center. And the loading also symmetry. So this is a symmetry. So what we need to do is just to get one side here, the bending moment, the shear force and axial force, then we can draw the diagrams for the whole frame. Because this is a symmetry problem, which is symmetry. And the other characteristic of this, the other special things of this is the loading here. Okay. This loading is like floating in the air. Okay. Before we have loading acting here. Now this loading acting like this. So what is the meaning of this loading? So this kind of loading class is normally we define for snow loading. The last one I show you the snow because after this room will snow. Okay. This is how we define snow loading. Snow. Okay. Snow loading is defined on flat area. So this is one of the example for snow loading. Okay. So how to consider this? In this example, I'm going to share with you how to consider that. Okay. 1023. Check statical determinacy, cut at the hinge there. So you can get conclusion that this is statically determinate frame. Next, to get the support reactions, this is a symmetry problem. So the reaction also should be the same here. This going up, this should be the same, half. That should be the same. And this should be symmetry. This should be same magnitude, pointing in opposite directions. So we make use of that symmetrical characteristics. We can get the reaction force faster. Or you can apply the equilibrium equation, take note of the hinge there. We can also solve this problem. So AX should be equal to EX, but opposite directions. AY should be equal to EY. So the total of this divided by 2 comes here, and the other half goes there. So that is, if you take advantage of the symmetry, we can decide this very fast. So after you know this AY, so you use the free body diagram of the hinge ABC, then you can calculate AX. You can calculate AX. Once you calculate AX, then you know EX. So this is the first step to get reaction force, but here you take advantage of the fact that this problem is symmetry. So this example here, after you get reactions, you need to calculate the axial force diagram, bending moment diagram, and shear force diagram. Here is to explain to you, we make use of the fact that this is symmetry. Just get half of this, and the other half we can obtain through proper. You just need to mirror it, flip it over to the other side of the axis of symmetry. Now, this problem is not symmetry. Okay, so you cannot use the characteristics. This problem, the structure geometry is symmetry, but the loading is not symmetry. So class, for a problem to be classified as symmetry, the shape must be symmetry, the loading also must be symmetry. Then only it is considered as a symmetrical problem, and we can apply what I discussed just now, the characteristics of the shape of the axial force diagram, shear force diagram, and bending moment diagram. So this, the shape is symmetry, but the loading not symmetry. You have this load here, but on the other side, you don't have that loading. Okay. So here, the main thing to show that once you know the bending moment here, you know the shape of the bending moment here. Once you know the shape of bending moment here, you know the shape of bending moment here. So only need to get this and this. So this is the meaning of the statement there. Now, the vertical part, I think class, you have no problem now. The vertical part here, if you cut here, then you use this free body diagram. Positive X shear, positive bending moment, axial force, we leave it later. Positive shear, positive bending moment, make use of this free body diagram. Then we get shear constant, and we get bending moment straight line. So this one shouldn't have any problem because so if you try to draw for that part only, so this is what we get. Here is negative constant and bending moment is negative 60. Straight line 0 to negative 60. Now, here, this is the special things about this part now. Now, class, can you give me another 15 minutes? I finish off this part, okay, before, all right? Because I say I want to stop at 10:29, but now it's 10:28, so if I talk very fast also cannot finish in 1 minute. If you are another 20. Next slide. Okay. Now, here, the main point here, which is different from others, other than symmetry, is for this loading, have to change to this loading first. You have to change to this type of loading, the 12 kilonewton per meter, which is defined on the projected length, distribution over projected length horizontal. Need to convert them into load which is distributed over the member. That is the first thing. After that, remember one previous example that we look at, you need to get the component of 9.6 kilonewton per meter in vertical, in perpendicular direction and in parallel directions. So after this, it's the same thing that we have seen in previous example. But here, which is over the projected length on this horizontal distance, must be converted to this load first. So how to convert that? That is the next step. So this is how we convert it, okay? This is the steps need to get to this, and then this one is the same as one of the example that we have seen. Get this component and this component, but you need to know what is the inclination of this member. What is this angle here? Okay. So how to get this is this is how we get. Okay. This 12 kilonewton per meter class is distributed over horizontal distance 4 meter. So you get the total load. You get the total, which is 12 multiplied with 4 there. Then you distribute it over the new length, which is 5. So 12 multiplied with 4, you get the total load. Then divided by 5, you distribute it over the member length. So this is the calculation to get 9.6. 12 multiplied with 4, the total divided by 5, you get 9.6 kilonewton per meter. So that is how we get from 12 to 9.6. But 9.6 now, class, take note, is acting on the member now. Acting on the member now. So this is the conversion, okay? So after that, you just convert them into perpendicular directions to the member, parallel to the member, okay? Now, this 543 class is not always 543, okay? Because in example, to make it easy, we always use 543. But this 543 is coming from this problem. So you have to take note the problem maybe 3.6, 8.7. So not necessarily all the time 543. 543 come from the problems. So this one, 5 meter here, 4 meter here, 3 meter, given in the problems. So we know the inclinations. So this angle is equal to that angle. So to get this, then you can calculate using the sine and cosine to get that component, perpendicular and parallel. So that is the steps to get the perpendicular, the green color one, and the parallel, the yellow, not the yellow, the golden color one. Okay. Now, this one is a bit more calculation to be done. So this diagram here, now we finish, we are ready to get the shear force now. So now this is important to know the shear force is defined in the directions perpendicular to the axis of the member. So look at the direction of the shear force now. S. So when we want to calculate shear force, we need to use equilibrium equation in that direction. So when you want to use equilibrium equation in that direction, all the forces which is not in that direction, you have to find the component. So you see there's this small arrow, these are all the component of this. This is a component of that. So that is why important to know the direction of the axial force and how to find this component. Okay, I will have a separate slide to the cat is coming. So how to get this, okay? So that one I will have a separate slide to explain to you. So you get the shear force to be in this equation, which is a straight line because this is a distributed load, UDL. Then okay. Now I forget because of the thing. Okay. Now class, I think I almost finished here now. I think now moment at cut sections, now, there are two ways we can consider, but the main thing, class, to remember is moment is force multiplied with perpendicular distance. So here, this moment here, this is from here, okay? This is 90 degrees, okay? This is 90 degrees. So moment caused by this will be just this one multiplied with this because the perpendicular distance is in these directions. Okay, 7.68 multiplied with x over 2, you get this term. And this one here, we can go back to the definition of moment. Here, we don't need to find this component. For moment, we can make use of this and this. But to take moment at this, you must find the perpendicular distance. Perpendicular distance to here. To find moment caused by this, you must find the perpendicular distance in this vertical direction until here. So this is the calculation that we use here. Now the x is defined in these directions. Okay, is still there, the cat? Okay. Now x is defined in this direction, x. So here will be, because this is pi 4, 3, so this become, if this is x, this become x 4 or 5 horizontal distance, this become the vertical distance. So 48, you look at that 48 there. 48 is this force. The moment at the cut section here will be, you need to get the perpendicular distance, which is this horizontal distance. That's why 48 multiplied with x multiplied with 4 over 5. 48 multiplied with this distance. For this one, the perpendicular distance will be from here until here. So it is 5 plus this distance. So that's why you have 5 plus this x multiplied with 3 over 5. So you simplify, we get this. So it is a curve. Okay. Shear is a straight line. Your bending moment is a curve. So class, one of the important things that you have to take note here is the basic concept of moment at a point. It will be always back to basic force multiplied with perpendicular distance. So we need to find perpendicular distance. So if I draw the shear force diagram, bending moment diagram now, for this part only, so the shear force diagram will be a straight line, and there is a point of zero shear there, and bending moment will be in this way, and we need to find the maximum bending moment where the shear is zero. So you have to find the XF distance there. So to find the XF distance, you go back to this you go back to the relations of difference in shear at 2 points is equal to area under the loading diagram, which is this one here. Then we can find XF. Okay? You need to find the location of zero shear. Then you substitute into these equations, then you get what is at the point of F there, what is the maximum value of the bending moment. Okay? So if you combine all, plus this is a shear diagram, we get one side. Yeah, we get one side only, then we can get the other side. And the bending moment diagram, we calculate only one side here. Then this side is a mirror. Just flip over here. So this is the bending moment diagram. The shear also, we get only one side, then we can get to the other side by following the procedure that we explained earlier for problem which is symmetry. Okay. The shape of shear force diagram and bending moment diagram for one half of the frame are obtained. We calculate that. And the complete shear force diagram and bending moment diagram are obtained through suitable inverting or rotations. The process of getting that shear force diagram for symmetrical problem and also bending moment diagram for problem which is symmetry. Okay, so this is the process. Get to that. We get the half first. The complete one is this. So what we do is you flip 2 times. Okay, you get to this dotted one first. Then you flip again. You get the complete one. Okay. You flip, then you get the one in dotted line first. That is not the final one yet. Then you have to flip again. Around each member, you flip it over the member, then you get the solid line one, and complete the shear force diagram. Bending moment diagram, the same thing. You get one side, and then you flip over, then you complete the other side. The last one is axial force diagram. Axial force diagram is obtained for member AB. Use that free body diagram, so you get Q negative 48. And for the inclined member, for this inclined member, we make use of this free body diagram. And again, you see there are a lot of components that you need to find. Everything because the shear is defined in this. So have to find the component of this in this direction, the blue one, the component of this in this direction, the red one. Because that is the direction of the shear force. So if you do that, then we can get the axial force to be in these equations for member BC, okay? So finally, this is the axial force diagram. We get from this side and this side only, from these equations, 48 negative, and from this side, it is a straight line. The starting value is this, the ending value is this. Then to get to this side, this is axis of symmetry, you flip it over, then you get the other side here, which is, this is negative, here also negative. Here negative, this also negative. So here, class axial force diagram, condition of symmetry is used to draw the complete diagram. So it's similar to bending moment diagram operation. Just look at the axis of symmetry, then you flip over the other side to get the complete one. Okay? Qualitative deflected shape. So this is a qualitative deflected shape. Bending moment diagram on the compression side, so we know which one is compression now. So this side should be compression, this side compression, this one compression, this one compression, but this one a little bit top one compression, compression. So based on that, this one is cannot move, this one cannot move. The angle should be maintained. So that this is a qualitative deflected shape. So this one bend like this, compression here. Then the one bottom part compression bend like this. Somewhere change to bending in this way. There's a hinge here. Then this side is symmetry. The shape, this side and this side, they are symmetry. So angle of rigid joint must be maintained. So take note of that when we draw qualitative deflected shape of the frame. Okay. So again, here I emphasize where is the compression side. It follows your bending moment diagram because we draw bending moment diagram on the compression side. Okay. So again, this one shows you how the member should bend so that the compression side is happen according to what the bending moment diagram will show. So this just to show to you bending moment diagram, if you draw on tension side, it's just you flip it over. Okay. So like this become like this like this is almost we are going to close the door. This one is open the door. Okay. This one compression side, tension side, just bring it to the other side, bring to the other side. This flip here, flip down, flip up. So you get this is the shape. Okay. Now, there's one advantage of drawing on tension side. When we design for reinforced concrete structure, we want to know which one is tension because that is the part where you should put the steel reinforcement. So when we design for concrete structures, it is advantage to draw, to know, to use bending moment diagram drawn on the tension side because concrete is weak in tension. So if you know where is tension, so we know where should we put the steel. Okay? We should put the steel close to the tension side because the concrete is weak in tension. This represent concrete member and this represent the steel. So we put the steel close to the tension side. So if you draw on tension side, so it's advantage for us to decide where should we put the steel reinforcement. But class, what we follow, the convention is drawn on compression side. Okay. Three more slides to go, class. Let me finish off this. So this is example of drawing compression side, drawing tension side. We just change to the other side. Again, this compression side, tension side, magnitude the same, only you draw on this side. But which one is compression remain the same. Okay, which one is on compression, it remains the same. This one remain the same. So this tension now you draw on the tension side. This one compression, you draw on the compression side. So this is one exercise for you to draw. If you want to draw on tension side, how should it look like? Okay. Now, we come to the end here. Then let me emphasize something on the, I will share with you this on e-learning, okay? So loading, there are these different types. So you need to know the direction of the loading. It is distributed over the member or it is distributed over the projected length. Okay, we see how to consider the case of distributed over projected length. But loading also can be like that, which is vertical over the member or perpendicular over the member. So there are different kinds. Okay. Then this is the slide that I'm going to share with you how to calculate that. So how you should calculate is this, you should always draw this line which is parallel to this member and this line which is parallel to this member direction of the S. Then if this is theta, this should be theta. Okay. Then to get this component here this is actually acting here. Okay, to get this component here, so after you draw this line, you want to get this component which is follow this component. So AX sine theta, you get this. And for this vertical one, to get this component, follow this. If this is theta, and this should be theta. Okay. So this angle, you should know how to relate them. Inclination of this member to this part here. If this is AY, and to get this, so it will be AY cos theta. For you to get this to be considered in the equilibrium. Okay. For horizontal, the same. Okay. For horizontal member is this, for horizontal Q direction is the same. Draw this, and you draw this. So this is AX cos theta, and this is AY sine theta in the direction of Q. So class, this is the one that I'm going to share with you so that you know in more detail how to get this. This is quite time consuming. Yeah, you should know how to proceed. Draw this line and draw this line, draw this line, draw this line, get the corresponding angle, and then see which component you want to get, this one or this one. Now, class, this is really the final one, okay? Now, when you draw shear force diagram, bending moment diagram, class, please take note of a few things. So when you draw this, so this diagram that you draw here, this one should be 90 degrees to the member axis. So draw like this, don't draw the shear force diagram in that way. The same thing here. When you draw here, this member, so this part of the diagram, this should be 90 degrees to the member. Okay. The same thing with bending moment diagram. Then bending moment diagram, if you take note at the joint here, whatever here should be the same over there. If this is 100, this should be 100, unless there is a concentrated moment here. If this is 100, then you draw this 150, then something wrong with your calculations. If this is negative 50, this should be negative 50 if there is no concentrated moment acting here. So that is one point for you to check. Okay? And at the pin support, moment should be 0. Okay? So draw the shear force diagram, bending moment diagram, draw it in a way which is proper. So this, when you draw this line, it should be 90 degrees to this member. When you draw this line, it should be 90 degrees to this member. Okay. So this is the thing that I want you to take note by looking at the bending moment diagram, shear force diagram, the same thing here. As you notice here, negative 560. So on the other side, also negative 560. Okay. Negative 560 is from this side. And from this side, we draw also negative 560. They should be the same unless there is a concentrated moment acting there. Okay. So these are the things that when you draw, when you look at shear force diagram, bending moment diagram, negative 100, if you draw from here, then this one also should be negative 100. They should be the same. And draw it 90 degrees to this member. Draw this one 90 degrees to this member. Okay. So I don't want to see bending moment diagram when you draw for this part, it becomes not 90 degree, which is it is not correctly drawn. Okay. It should be drawn 90 degrees to the member, 90 degrees to the member, 90 degrees to the member. Okay. Same thing here. Okay. So class, I take extra of your time, and then until the cat also come in. Okay, the cat supposed to be, the door is supposed to be locked at 10:30, so cat cannot come in. So now the cat, where is the cat now? So class, thank you very much for staying extra time. So this additional one that I show with the PowerPoint, I will share on the e-learn so that you can go through that again. Okay.